Thank you very much, Chris. So I'm really excited to get this chance to talk to you today. I want to talk to you about growing trees with recursive enums in Swift. And I, of course, want to do this in a functional way. My talk's not going to be like as theoretical and as like hardcore functional maybe, but I really want to show you some cool examples of what you can do with functional with a functional paradigm and how you can solve some like complicated problems in a very elegant and very performant way. So at the end of the talk, there will be like cool examples. So if there's a little bit of like code in between, then you like have to bear with me for the code to see the good stuff come up. I didn't come up with all of this myself. I basically combined the chapter 4 or chapter 5 from the Functional Swift book by Chris and Florian, and I needed to implement a so-called KD tree. So a KD tree is, I will get into what this is later, but I basically combined those two sources. I looked at how the KD tree is built, and I built it in the way described by Chris and Florian. To go over the contents of my talk today, I will shortly recap the types that we have available in Swift. I will also look at trees in Swift using enums in general, like build a very, very simple tree using these recursive enums. And afterwards, I will explain to you this KD tree as a practical example of this. And afterwards, I will show you how performant this is and some pictures of some nice examples. So next up, recap of types in Swift. I guess everyone here is familiar with the fact that we have value types and we have reference types. The most used ones, obviously, are the struct and the class. But then there's often overlooked enum, which is a first-class citizen in our world of like types too. Many people still use them the way that we're used to them from C or from Objective-C, but you can do much more with them, which is what I'm going to focus on. And also we have closures, which are also a reference type. I just like put it up here to be complete. I'm really assuming that everyone is familiar with the difference between a value type and a reference type for this talk, because some people say functional programming may be also dubbed value-oriented programming, because we don't want to share state, and functional types, value types are the ones where we have immutability and where we have this copying behavior which we need for functional programming. And if you're not sure what really the difference about value types and reference types, what this is, I recommend Googling this and like reading through a tutorial, or even reading Chris' book about functional programming, this, or Advanced Swift, or what reference you want to have. So we focus on the enum. Now, if you think back to your Computer Science 101 class, the way you would create a tree there, I took an example here from a Wenderlich tutorial. You know, you have your tree, there's like some nodes, the nodes can have children, and you're gonna do something with them like sorting or having some spatial thing, and you would usually implement this with like a class where you have a node and you have the children, and if you add something, you add a value to the children nodes, and it's it works. It's the way we always did trees back in C days, back when we learned this, but also it's not very functional. As you can see, there's like all these vars, which means there's lots of mutation going on. We basically operate on this one place in memory, and we always move stuff around. It's not safe, it's not elegant, and like, of course, we want to do it in a functional way. So how can we do this better, or how can we do this in a functional way? Not better, like this is not wrong, it's just like not what we're here for. So we can use enumerations. So enumerations in Swift, they have some stuff that in other languages we wouldn't have. So you are all familiar with the typical enum that we all have used before, like having a bunch of cases, and each case is represented by maybe an integer or a string. It's very basic. So then we already start feeling it. Maybe when this thing fails, we would like to have some knowledge. We would like to know what actually happened. So we extend this and say, okay, we add an associated variable, we add a variable error. And here you can see how the enum suddenly becomes like a full, with this additional properties, becomes like a full-blown type, because we can add variables to this enum, we can store values in there, we can even give it functions, which we'll do later. And so that's great. Obviously, we can also make it generic. You see the familiar optional type there. That's exactly how it's implemented in the standard library. And you can see that now this associated variable is generic over this type T. And now for the next step, I'm going to show you the basis for this talk today, which is the recursive enum. And we need one key code word, or one word, in this case, the indirect. This wasn't available in Swift 2, I think. In Swift 3, it was added, or maybe in 1 and 2. In any case, now we can very elegantly define a tree enum, where the case of a leaf is sort of similar to the case of none that we had before, where there's just nothing. And the case of a node, we need to say indirect, because we're actually using the type itself inside the node for the left and the right side of the tree. This is sort of similar to what we've seen from the Computer Science 101 class, where all the children had the same type of the class that we had there. So there's this familiar thing. Again, we are referencing the type itself, and we're using the type itself in its own variables. That's why recursive, that's why we're talking about recursive. And this is a very simple tree. Important to also note, I gave the element the necessary, made it necessarily comparable. Like I made sure that it's conforming to this protocol, because I want to do something with this tree. And if we just had a random element, we could do random trees, but then we wouldn't like use it for anything. We obviously want to do something with it. Comparable is like a very simple example. I will then extend this to go into a much bigger, much more complex example. Yes. Now, recursive enum, if we wanted to create a tree with a single node, we can do that. We can customarily maybe write a free function for this. So we say, okay, now create me a node with a single value. And so on the left side, there's a leaf. On the right side, there's a leaf. And in the middle, there's a value. It's like important to distinguish. There are some trees where the leaves have elements too. In our case, the leaf is really this empty value. And there's a value, yeah. So far, this is clear. Everyone's like, yes, it's still in the morning, so maybe you're still sleeping. So now I have a playground for this. If you want, you can check out the short link there, where we're going to want to play around a little bit with this tree that we have now created. And we want to see like how this feels by touching it ourselves. So I'm going to exit here. I have to be a little bit careful about the machine. Switching to mirror mode. Oh, this looks nice. And switching to Xcode, full screen. So this is this single value that I had before. Let's say, for example, we want to create a tree with a single node. We say a single, and maybe let's add the node 7. I have a little bit of I made it conform to debug description so that we can have a little bit of a nice representation of how this tree looks. So up there's a 7. Now, of course, like nodes, like trees with a single node are not very useful. So we want to extend this tree to also be able to add new values into it. So this extension, I wrote like a simple thing here, which of course doesn't make sense either, because we just return a single value again. We want to like add code into this method. But important maybe before we start is that we are going to write a functional tree. So we're not going to mutate it, but always when we add something, we give back a new tree. So in this case, we use inserting. It's sort of similar if you have worked with Swift already to the sort and the sortet. In this case, when you add a value, then you would be inserting because it's a new tree that we, yeah. And important to note is because of this tree is an enum, we usually or customarily use a switch case to iterate over all the values when we create it. So let's do that. So we switch over self. And first case is, of course, a leaf. And now if we have a leaf and we add a value to a leaf, the thing that we would want to return is the single one. So actually we can just take this one here. Wow, this is very loud. And then we already have leaf is an empty one. Then from empty, we go to a one value tree. And so in the case, let's add another case. In the case of a node, we just, so this is the case where we would add a value to an existing node. So we have the left side, the value, and the right side. And of course, we want to put these into variables. So we need to use a let here in order to get this. Then we don't need a default anymore because we have covered all the cases. And so what are we going to return here? Well, we sort of need to return a new tree based on this, but first of all, we need to have some structure in this tree. And as you heard before, my tree uses elements which are comparable. I did this for a reason, and the reason is exactly that now I can check, okay, is my new value smaller than the current value? And if this is the case, I return a new node, so we can do tree.node. And if it's smaller, we insert the new value on the left side. So we take the left side that we have, and we insert the new value. The element will just be the same element as before. The right tree will also stay the right tree as before. And then, oops, a little bit loud. Else, we return this. And this return we don't need anymore. And of course, then we need to move, if the value is bigger than the current value, then we put it on the right side. This is, I mean, I hope I'm not boring you too much. This seems all very simple, maybe. Okay, cool. So now we wrote our inserting function. Like you can see, it's already very simple. There's a switch case. We go over all the nodes and we do what we want to do. And like, let's play a little bit around with this. So let's trade in tree 1 based on the tree we had before. And we are inserting a value number 2. Hopefully let's see what we did wrong. Well, it wouldn't be a, oh yeah, cool. So now we have the 7 that we had before, and there's a 2 on the left side. And let's maybe do this again. Tree 2 equals 3 dot inserting 10. Now, of course, well, what happens here? We are doing this on tree. Tree didn't change. So what we really maybe want to do is like, use the one from that we just created. So tree 1. And so on and so forth. We could like create this larger tree. And as you can see, like the structure would just like get bigger. Do you want to create another function? I think we're well in time. Cool. So for example, in the collection, it's kind of useful to have maybe a count function. So if we wanted to add a count function to this tree, we would again do the same thing as we did before. We say var count, and we say there's like integer amount of elements in the tree. And we do again switch over self. In the case of a leaf, so how many elements do we have in the leaf? Well, none. And yeah, maybe we can just copy the node here. So a node would have all the elements from the right side, all the elements from the left side, and the element in the middle. So it's very simple. Again, left count plus 1 plus right count. Very easy. The point here is really to exercise every time we write a method for this, we need to be recursive. So we always need to go into the elements that are like below the current one. And we also need to usually iterate over like have something for the leaf and have something for the node and check out the values. So maybe we can test this by saying, okay, tree 2 count, and we can do tree 2 inserting whatever 9 count, and then we have hopefully yes, very good. So our count function works. If you insert something, then the new tree that was created has 1 element more. Very good. Just checking my screen is still recording. Very good. So now back to the talk. Or anyone questions about the playground? This was a very simple. It's the morning, so my playground is very basic. So let's swipe good and back. So what have we learned? We had this tree. That tree had a leaf and a node. We created a free function to create a single noded tree, and then we inserted values here. Maybe again, like what we just did in the graphical representation, because for the people who are not so familiar with functional programming and with like value types, the point here really is that we have like this piece in memory we insert to, and we get a new one. And that's why the color is different, because this is like a new object that we get. And again, we inserted 10, and then we created a new one. So by that time, the people here who are like I come from Fortran programming and from C programming originally, so I'm very like close to the machine. I'm always about performance and my numerical algorithms, which needed to be really fast. And if I looked at this without knowing about Swift, I'd be like, what the hell is going on here? Isn't that super inefficient? We're like copying this thing. Imagine we have a tree with 1,000 nodes, and we add a value, and then we get 1,001 nodes, and we get like 2 of those in memory. It's like, this is horrible. Isn't it like super slow? Well, the memory impact, like the CPU impact, wouldn't this be? Now Swift helps us here. As you probably know, the Swift compiler delays the copy as long as possible. Like only in the moment when we actually need to make a copy, it will actually do the copy in memory, so that we feel like we're programming in functional, but the compiler is actually only doing this copy at the latest possible point. So for example here, as long as we are not like, now we're using tree 2, but as long as we're not using this tree 1 anymore after this point, what will happen is that the memory is just going to reuse the memory from tree 1 and just add this in there. So somehow in memory it will look like this. I am not a compiler expert, so I just know the Swift compiler like writes code for this that is like very efficient and delays this copy in the last moment possible. If you want to know more about this, there's the copy on write explained very well in the advanced Swift book in this chapter. They do this much better than I can ever do it. So that's that. Now, of course, I told you that we're going to have some cool examples in the end. So I have like a break and I want to talk to you about space. Who are here like space? Yay, me too. That's really cool. And in particular, I want to talk about spatial data. Like in my example that I needed to solve, I had spatial data. So what does this mean? Well, for example, imagine you have a map and you have like a bunch of points on this map. In this case, I found this is like the accidents that happened in New York over a certain amount of time. And you can see there's many little nodes. Now, if you would like, I don't know, like I know there's you would want to write an app that like you can look at, okay, what was the accidents that happened in a certain area? And now if you want to tap on this, like if you have this as a screen thing, then you tap on this, like one problem is obviously, well, do I want to have like my large area of all my nodes and then I go through there and I'm always checking, okay, is this very close to the one that was currently tapped, to the point that the user tapped? Is this very close? And I'm linearly going through my array and like always trying to find, and then at the end, you know, maybe if it's 2,000 nodes, I'm iterating for this whole array just to find the node that is closest to my point. I don't know, this doesn't seem very efficient to me. Same thing, obviously, I was talking about space. Another example would be if you had data like this. You had like a star map and you have a bunch of stars there when you want to tap, and then you want to know which is the one that is closest to the position of the finger where I tapped. And again, you have sort of spatial data means you just have like a coordinate system where every point corresponds to, in this case, a two-dimensional thing. So we need a solution for that. We need some solution how we can operate on this spatial data. So the solution and one common solution, there's many others. One common solution is the so-called KD tree. KD tree just means that we're like in a k-dimensional space. In this case, like in the beginning, let's talk about two-dimensional space, but you can have like any dimension you want. Like me as a mathematician, I don't care how many dimensions. And the point here is that we want to make sure that sort of like this is for me, this is the simplest way of explaining this KD tree. Like we really want to make sure that our data structure has the points in the data structure in a way that it corresponds to how the points are related in space. And like a proper definition is like we want to partition space based on the metrics of the point that are being added. And partition just means to like cut the space into pieces. You can think about it if you had like a static system, you could have like a checkerboard and say, okay, everything has this little quadrant where it lives in, but we don't want to have this, like this would be static, and then if all our points on the right side, we have all these like checkerboard things on the left side. We want to base this like cutting of the space onto the actual data that we get. And metric just means a way of measuring those points, like how they are close together and how not, for those who like don't know the fancy words. So like as an example, maybe let's see, we have a KD tree here where I did a little bit of an illustration, and here the point A is sort of a little bit in the middle, and this will be our root node, and then there's a point B and C that is sort of like in the middle of the other two, of the left and the right side, and then these points are in there. So how I created this tree, I will go into a second, but the point here is really just to illustrate The left side, the spatial data, sort of corresponds to the way this tree is built. So sort of like one thing fits to the other. And we're going to use that to write algorithms on it. Now Wikipedia has a pseudo code for how we would create a KD tree. Of course, the KD tree itself we wouldn't create by like adding one value and then adding all the others, because then we'd have like a random tree. The point is here that we would need to have like, yeah, some code where basically looks maybe a little bit much code in one slide. The point here is really it's very similar to what we did before. Basically, we take the one that's in the middle, and then we take all the ones on the left side, put them on the left subtree, and we put all the ones that are on the right side, put them on the right subtree. The important part here is that we're doing this by the axes that we're currently looking at. So in 2D, we're always going, okay, first step, we're going in the x-axis, second step, y-axis. Next step, we're going to the x-axis again. If we had more dimensions, we would iterate over all these dimensions while we're going into this tree. Before we had comparable, which just means we were technically a 1D tree. So the tree that I showed you just now on the demo was a 1D tree, and now we're going to talking about k dimensions. And maybe as a demo, I did a little bit of a, so yeah, this is my framework that I created based on this, and it's open source available on GitHub. But I want to show you inside this framework, I have a bunch of unit tests, but I also have test examples. And in the examples, there's a visual representation. Yes, QuickTime. So now we need to be very careful, Brandon tells me. New movie recording.
Go back to mirror.
Yes. And now, yes. QuickTime, yes. Need to be very careful because we're already recording. No! Oh, maybe no. What? Yeah, it was something with the, we lost recording? No,
No, we're good.
It's all good. So maybe as a representation of this algorithm, let's take some random points here. Can you see my points? Yes, you can.
Yeah.
Very good. I maybe can put them a little bit in the middle. So this is what I'm doing on my phone. So now, first we go in the x-axis direction. We look for the point that is currently the median. Median meaning the point where on the left side there's an equal amount of points on the right side. Obviously now our data set is sort of like on the right side of the plane, so our median will also be a little bit on the right side. And then once we have that point, we halve the plane on this axis and look in the other direction. So now we have the points on the left side going on the left subtree and the right side subtree. And now, again, we look for the median point on the left and the right side based on the y-axis. So there you have your median points, and we cut the plane, and then we look again for the median points on the x-axis, and the same thing again, and the same thing again, and then we have our tree. Maybe like we can do this in a larger example. Again, x-axis, find the median point, half the plane, y-axis, find the median point, half the plane. So this looks very simple now. If you, the core part here is though that why we do this, obviously we have to do a sorting of all the points by the current axis. So there's a little bit of a performance impact. I will get into this in a second. But yeah, you can see, well, just this nice, I like nice core graphics animations. So I made it here to show. And I think for me, this like animation shows very well how this algorithm works. And now what we can do with this, of course, is if we have this tree structure, we can then, for example, say we want the k nearest neighbors, click somewhere and find, okay, what are the nearest neighbors to this? I will get to this again, but since we have the phone open right now, you can just click somewhere and then you find the nearest neighbors, and this is like lightning fast. Maybe going back, tree, find axis. The important point is this algorithm that we just saw on the Wikipedia page. Oh, this is not a good one. Let's have this one. This algorithm just saw on the Wikipedia page was maybe complicated, but with the graphical representation, it's really not that hard. You just like always half, find the medians, and next step, half, find the medians, and next step. This is 2D. You can do this in any dimension you want, of course. Yeah. You can check this out on the GitHub page, just like if you clone the app and then you run the example app, this is exactly what you get, and you can like play around with this yourself if you are interested. I will keep the movie recording, go back to the slides. Well, Yes, this was this demo. And now, how would we implement this KD tree in Swift? So it's the same thing we had just now with the very simple tree. Instead, the element is no longer comparable. I made it a KD point. I didn't want to call it KD tree pointable. It's really what it is in this case. It's a KD tree point. Yeah, the structure looks really the same. One thing that is important to note here is I'm storing the dimension. This is sort of like this step as I'm going deeper into the tree. Maybe I can show you this here. So for a CG point, for example, what I would do is like I store this point in the value, and then I have the dimension there. And like as you get deeper, I iterate what is dimension. This dimension value here is just performance optimization thing. I didn't want to like carry this around during the algorithm with me. So I end up storing it in the value. It's just an integer. It's not going to make our tree significantly bigger, and it does help with performance. Yeah, this is the same thing we just saw. Tree of 3 values. These are three two-dimensional points. My KD tree point protocol. So if you had some data and you wanted to use this, you need to make your data conform to this protocol. It looks a little bit awkward. I don't know if you guys have suggestions on how to make it prettier. I'm all open ears to make a pull request or something. Point really is, all I'm trying to say in this protocol is like every point needs to have a number of dimensions. I need to know how many dimensions. So there's a static variable that tells me how many dimensions I actually have. And then you have a function where you can get one dimension of this. In this case, it needs to be a double. So like casting to double from the CG point there. And then I'm taking the square distance. You also need to tell me the distance function you're using. In this case, it's the Euclidean distance without the square root, because as you know, square roots are expensive. We don't actually, when we just want to compare, we can always just compare the squared ones. You could use a different metric. You could use, we're in Manhattan, the mathematicians have a Manhattan metric, which is just the maximum metric. Manhattan's next door, but my point. So that really depends on the data you have. I will show you one example where I used the maximum metric in a second. The only thing, so now we had this like fancy algorithm we had from the Wikipedia page, which is basically explained in Swift here. If we have if our values are empty, if we created a tree without any values, we just trade a leaf. And otherwise, we have to look in which dimension are we currently splitting. And then we have to sort along this dimension our points. Then we can find the median point, and then we just do a left tree and a right tree. And those are just taking like the 2 parts on the left and the right side. Very straightforward. And since it's a functional algorithm, the left tree and the right tree call the same method and get the return type. And then we're returning the combined of like the returns that we got before. And we get a tree as a result. We had the insertion method that we just wrote in the single example. This is like the more complicated example where we, again, basically test, is it on the left side? Is it on the right side? And then we check and then insert it on the left and the right side. This is really the same thing we just did for this one-dimensional case just now. Okay, well, everyone's nodding. But one thing you might have seen here when we created this tree is we need to do this this sorting. So that's probably where we lose most of our time, and I'll show you this later. What have we gained with this? Well, we can write like algorithms like contains, insert, remove. They're all O log n, but this is what you expect because that's just what the tree is about. Cool part here is that we also get the nearest function, and this nearest function is also O log n. Show you what this means in a second. Same thing, nearest k is also O log n, so you can get the k nearest values to a certain point. This is really cool. And of course, I conform with this tree to a sequence, so you can do all the things that you know from sequences, and you get all the Swift functions for free, which then operate on this tree. And as I said before, the init method depends on the sorting algorithm. I think Swift is using the insertion sort. So this is like a little illustration for the nearest neighbor. We will have to deal with this insertion sort at some point. By now you're interested, okay, I created this, run for all of this. What's my performance? Well, this is nearest neighbor. This is for my 4-core MacBook, although it's not a parallel algorithm, so the MacBook doesn't matter so much. It's actually very similar performance on the phone I went up to 5 million points here. As you can see, the time that it takes to search for the nearest point linearly rises linearly because you have to go through the array. But if we use the tree, we only have to go into the subtree where our point actually lies. So when we do the nearest neighbor, we basically do the same thing as we do when we insert. We always check, is it on the left side, is it on the right side? There's a little bit of tricky things involved when your nodes might be on the left side, but then they're still on the other axis, on another axis. But you can look into the code. The point here is the green points are so close to the x-axis for the amount of test examples I made in this another graph. For how long it took. So this is really for the amount of points here. I run an example where I created a random big set of points, and then I searched for the nearest point to a given point. And you can see, I don't know, this is so little time that until 1 million points, it just fluctuates because sometimes you're closer to an existing node and sometimes you're not. So it's lightning fast, I'd say. And this is really when you have your algorithm. I also show you this in a second. And you want to tap somewhere, and when you want to tap with your finger, you don't want to have any delays. So you want to show the user the interface feedback. And if you had maybe on your phone, you would only have 1 million points. And as you see, if you have half a second of delay until the actual calculation, then after this calculation, you still have to maybe draw something on the point you tapped. So it's not great. That's why you need this tree. Same thing, you can do a range search. It's very similar to the nearest neighbor, where you can say, okay, give me everything that's in this little quadrant of my space. And again, this is for 2D, this is not so hard, but for 3 dimensions, any dimensions gets harder. And there's again some performance here. This is for this range search. And you can see even for 5 million points, what I did is here, I have get me the points in a random 0.1 quadrant of a large plane of 0 to 1 squared random points. And for 5 million points, this is 3 seconds or something. And of course, you have 0.2 seconds if you use the tree. So again, very efficient. And you can really build cool apps with this. And maybe just before I'm running out of time, but I'm finishing. Yes, aren't we forgetting something here? Well, I talked to you about this insertion sort. So there is a little bit of, there's what do you say, there's no free lunch or something. You have to spend a little bit of time in the beginning where you create your tree. So obviously this is linear because you have to do the search now. And actually insertion sort is technically n squared. So the Apple insertion sort is very efficient, but it's still basically, if you look at the performance analysis, at this point, this is 99% to insertion sort to find the points. And especially since we always need to insert the left side, the right side, and then we sort by this axis, and then we sort by this axis again with the subtrees. Insertion sort is quick about it because most of these points will already be sorted at the point when we sort them. So, and then it's very efficient. That's why it's not really n squared here. But it's still not, you have to pay this. But in an application sense, I would say if you write an app, then you probably have some loading screen while you're loading your database, where the user is expecting, okay, now I'm loading your database, now this tree is great, and afterwards you can tap anywhere you want and it's really quick, rather than opening the screen in a split second and then having to wait every time you tap. Of course, we are writing a functional algorithm, so we can get better by writing this algorithm in parallel, because one great thing about functional algorithms is if we return the types all the time, we have no sharing of data, so we can easily write this in a threaded way. So if you look at this line that I had in my initialization, you can clearly see the let left tree and let right tree we can do on 2 different processors. And I did a performance analysis just last night, or 2 nights ago, I did a really quick implementation of just these lines up there with some semaphores. And then if we use this on 4-core PC, in the 4-core Mac OS, we actually see that we get nearly 0.3 of the time that we took for the unparallelized version. And on the phone, we actually get exactly half of it. So in the phone, I used the 2, it's a near perfect parallelizable algorithm. Great. So just a little bit of because obviously this is very fast. You always have to, if you do a lot of optimization in like I said, C++ or something, how much effort was it to implement this? How much effort is it to do all these performance analysis? Well, I can tell you it was not a lot of effort. The whole tree including all the documentation of like the method highlighting, is 291 lines. This is for creating the tree. The k-nearest neighbor algorithm is 135 lines of code, and this range search 47 lines, and conforming to sequence 51 lines. So this is like, you know, this is less than the typical model view model that you would implement in your app just to get this whole algorithm going. So for me, this is really the great part where I've showed you this performance thing, and like we can write an algorithm that's elegant, like uses little lines of code, and at the same time is super performant. And that's for me the great part about Swift, and that's a great part for me about functional programming. And I told you that I'm going to show you, I'm nearly done, I'm going to show you some cool examples of this. So what are cool examples? Well, there's a thing called tessellations, which for me just means filling the plane with objects. I needed to fill the plane with sort of random objects. So what I did is like I created pictures like this based on KD trees. I can also show this to you in the app in a second. Similarly, there's this thing called n-body problems in physics, where you would extend this algorithm slightly by giving, you know, imagine you have this like, I don't know, it's a lot of stars, or lots of solar system, and there's like all these like objects in there. And now if you wanted to really calculate the force pulling on one object, you'd have to calculate, because every body attracts every other body, as we know. So we need to calculate the forces between all these little points up there. It's like n squared problem, because like with number of points we have all these interactions. So what we can do if we store this in a sort of tree structure, we can sum up for all the like subtrees, we can sum up the center of mass, and then we can calculate the force pulling on one body in this little blue corner just to the center of these like other subtrees. So that we can do this in an efficient way using this tree. So there it's not about nearest neighbor, but by adding maybe the center of mass and the amount of mass we have in one subtree, we can make this even more efficient. You know, if you wanted to re-implement Kerbal Space Program on the phone, you would maybe use something like this. Of course, I needed it for a side thing where I have a medical startup with some friends in Berlin, and we needed something to make pictures like this. So who here cannot read the text? Okay, you might be slightly colorblind. So this is the point here is that like, okay, there's a can you read this written on there for those who can't read it. And the idea here is to measure how well people perceive color. Huh? Yeah, the perception. Yeah, I mean, the colors, yes, you have to be a little bit, maybe it's not this much, yeah. That is visible. Well, I wanted to have something that like, yeah, it's not too easy to see. So this is basically false in this tessellation perspective. And what I did here is I just sprinkled, first I did a random tree based on random nodes, and then I made it form into bubbles, and then I added some random bubbles in there. And of course, every time you add a new one, what you want to do if you want to create this randomly, you would like pick a random position, choose what's the nearest one to this, what's the existing one that is closest to my position, and then calculate the distance that you have to see how big you can make this one. Okay, yes, I'm nearly through. Like this is 3 more slides. Okay, so recommender systems are a great way. You know, a recommender nearest neighbor here just means the product you might also be interested in. Imagine we have a car, we have a bunch of values. I don't know anything about cars, so I just made up some values. I guess these make sense. But you know, you could compare, if you look at one car, you could compare them by these values and find like a car that is very similar. Further applications, maps, the points of interest that we have, like the accidents, and machine learning, we can do this facial recognition. We can have a large data set of faces that we can put in our tree and then we can compare them. There's financial fraud detection. Really, the last demo I just want to show you because I think it's really cool, and I still have the QuickTime running. Yes. No. I think I went twice. Yes. So we had this random tessellations thing that I said. This is like a random tessellation that does not use the Euler metric, but the maximum metric, because we're talking about squares. So this is just like, and you can see this is really quick. Like you can build this one. And now the other example is a star map. It takes about 3 seconds to load the CSV data of 120,000 stars, and then it takes about 3 seconds to create the tree. And now this is basically, it's set there's actually like 7,000 stars in this picture, but a lot of them are very, very small because it's a data set of like all the small ones that you have very closely. It's a HUC database. It's on my README in the thing. But the point here is like I can tap somewhere and try to find, like, let's see, I'm trying to hit this one, but my fingers are a little bit fat. Yes, there we go. So this is like a named star, but you can see, like, when I tap somewhere, the response is immediate, and we can see what's going on there. And this is 7,000 on this page just now, but it's 120,000. Like, and you can use the range find to give you all the ones in a certain area, and you can use the nearest neighbor to click on one. And this was this demo summary. We looked at value types and functional programming. We looked at how we can use those value types to create a tree structure based on enums. We looked at an example tree about these enums, and we browsed some potential applications of this. And this is the page. If you have questions, if you want to improve it, I would be very happy about this. And it's my my Twitter handle. And thank you very much.
We have like 2 minutes for questions.
Okay.
I could listen to this for hours, but we have other speakers as well.
No, sure. That's why I sped up at the end a little bit.
So, any questions?
I had a question about how you were generating the description of the tree on the first playground, brackets and the leaf and everything. You have that code?
Yes. Yes, it's in the recursive enum, the GitHub. When I had the playground slide, if you look in my GitHub page, there's a recursive playgrounds, the recursive tree playgrounds, and it's inside the sources of the. Yes, it's nice, no? One thing maybe I didn't say, really important for trees is also that you think about balancing of your trees. So if you add or remove trees, in my case, the removing is balancing, meaning if you remove one node, then it looks for a replacement node deeper in the tree and replaces it. Even though with this algorithm, the removing is still O of log n. But if you insert something, I'm not rebalancing the tree, which means that if you add a lot of nodes after you've already created your tree of like 1 million nodes, and if you now add a ton of nodes, 1 million ones on the left side, then your algorithm for nearest neighbor might not be efficient anymore because you created this. There are other trees, oak trees, and quad trees that like are B trees that are like rebalancing when you insert something. For my applications, this was not necessary. I needed a fast insertion function without balancing. That's what I did. But if you want to implement a balancing one, then it's also up to you. Yeah. I put a few semaphores in there. I basically had the code looks a little bit ugly because I just created it 2 days ago. It works. I checked it with my unit tests and everything, but it is a little bit like you create one semaphore and then you dispatch for the left tree, you dispatch for the right tree. In each case, when they're done, I said semaphore signal, and then I did semaphore wait 2 times, and before it creates the tree based of these 2 subtrees. It's not very pretty. Maybe I can optimize. That's why I didn't show you this yet. But it works, and it's also functional. And it's the great part about this is like I took like half an hour to write with the semaphores to write a parallelized version because we are writing it in a functional way.
Thank you.